Welcome to the final lecture for Math 1111, Section 6.7, Exponential and Logarithmic Models. So we have come a long way this semester, everything from learning what a function is to now studying these two types of functions for an entire chapter, exponential and logarithmic functions. So this last section puts all of the information from Chapter 6 together and has you applying it. So you have to know how to solve logarithmic and exponential equations to be able to apply them to given situations. And for those of you that are pure science majors, this is probably going to be very interesting and useful to you because you will be seeing situations like this in your future career. So let's go ahead and get moving forward. Okay, so at the beginning of this particular section, we are reminded about the exponential growth and decay model, which you can see the equation for in the center of the page, or well, center upper page there. But your book says that in real-world applications, we need to model the behavior of a function. In mathematical modeling, what we do is we choose a familiar general functions with the properties that suggest that it will model this real-world situation that we're dealing with from data that we collect. So in the case of rapid growth, and actually rapid decay as well, we may choose this exponential growth or decay model. And our choice of functions to serve as a mathematical model, like I said, we often use data points gathered from observations. So this is real world data that we use in these circumstances. And then what we do is step back and say, okay, what kind of general shape can we think of that seems to fit this data? And then we take points from that and develop the mathematical model from there. So don't forget, exponential growth and decay have two distinctive shapes. One obviously being a rapidly increasing function, the other one rapidly decreasing. So it is important to remember that although parts of each of the two graphs seem to lie on the x-axis, they are really a tiny distance above the x-axis because of their inability to actually ever equal 0. Okay, so just a reminder of what these functions look like and a few key points on each of them. So this is the characteristic. These are the characteristics of the exponential function, a sub 0 e raised to the kt. Now, I'm not particularly fond of how they wrote that e in the equation up at the top right there. So I'm just going to make sure that you realize this is this e we're talking about, the natural base. So it's written correctly here. All right, so don't forget these are one-to-one functions. They have horizontal asymptotes at the x-axis, which is the horizontal line. Y equals 0, domain is negative infinity to positive infinity, range is 0 to positive infinity. There are no x-intercepts because they're never actually going to make it to the x-axis. There is one y-intercept at the point 0, a sub 0. That is your initial amount of whatever substance or population that you're looking at, a sub 0. If your constant k is greater than 0, it will be an increasing function, meaning exponential growth. And if your K value is less than 0, so if it's negative, then we're dealing with an exponential decay function. I also have a couple of other key points noted on here, and we'll look closer at that with this first example. Okay, and I apologize before I get started on this particular problem. I forgot to include a graph on your set of notes, so you'll just want to hand draw in a graph near this problem on your physical set of note sheets. But let's go ahead and get working with this particular problem. So we're told that we have a population of bacteria that doubles every hour. If the culture started with 10 bacteria, graph the population as a function. Well, we have to have the function to actually graph to begin with. So we know that it will be modeled by our exponential growth and decay model, which is y equals a sub 0 e raised to the kt. So with this particular model here, our a sub 0 is our initial population at time 0. And then my constant, my K value, is given or gotten rather by is gotten by plugging in a given point, which every point in this particular plane here has T for time in hours as listed in the problem there, and then our population total will be our output value. So what we're going to do is take a given point, we'll solve for our constant, and then use that constant to write the equation for this situation. So let's take a look at the information that we're specifically given for this problem. Okay, so we're told that we started with 10 bacteria, and we also know that we double every hour. So for every 1 hour, we double our bacterial population. So our A sub 0, our initial population, is going to be 10. That's what we're going to plug in. But then we need to have one other point to plug in for T, and our population at that time T, which is Y in this case. So the only thing we have to go on is that it doubles every hour. So if we started with 10, after 1 hour of growth, the population would have to be 20. So that's where we get that other set of values from, that it doubles every hour. So after the first hour has completed, we should have 20 bacteria in that population. Okay, so now we're just going to plug everything into its place. So I have 20 equals my A sub 0, my initial population 10, multiplied by E raised to the K times my time, which is 1. From my 1 hour later, we have 20 bacteria. So now I just need to solve for K here. So to solve for k, I need to isolate my exponential expression first. So I'm going to divide both sides by 10. And I get 2 is equal to e to the k. I now come back and take the natural log of both sides. That will allow me to bring that k value out front as a coefficient. So now I have on the right-hand side that the ln of 2 is equal to k times the ln of e. Well, the ln of e, don't forget, that's just multiplying by 1 because I'd have to raise e to the first power to get e. So really, now I know my k value, my constant, the ln of 2 equals k there. So now I can plug that into my model and have the equation that models this situation. Okay, so now that I have found what my constant is for this particular model, I can write the model that will give me the opportunity to choose any hours past the initial population growth and see how big that population is. Or I can look at it the other way and say, well, if I have a population this big, how long has this population been growing? So I can either solve for the time or I can solve for the population size. And here is the equation. So let's see, I've got my constant here, and I already had my initial population size here. So I just need to fit those into the mold of my model here, which is y, or population size, equals 10, my initial population size, times e, the natural base e, raised to the, I'm not going to put k because I know what that is now. It's the ln, or the natural log of 2, and that's multiplied by my time. And so I'm going to leave that as a variable so I can plug in and figure out at different times how big the population is. So the ln of 2 times t. All right, so now that we have our model, it is not too difficult to find 3 key points to graph our exponential growth function. So we have our model, y equals 10e raised to the ln of 2 times t. And I have key points, which are given to me on this graph in its general form here. So I have the key point -1 over k and a sub 0 over e. So that first key point for this particular model would be -1 over the ln of 2 and 10 over e. And when you put those into your calculator, since we're putting this onto a graph, it'd be much easier to have it as decimals. So I put this into my calculator and found out that this is -1.443 and 3.6788. Okay, another key point that we're given is 0, a sub 0. So that's 0, 10. And our last key point, 1 over k, a sub 0 times e, instead of being divided by it this time. And for my particular problem, that's 1 over the ln of 2, and my y coordinate is 10e. And that's understood to be e to the first, by the way, for when you put that into your calculator to multiply. And when I put it into my calculator, I got 1.443, 27.183. Okay, so now we're ready to put this onto the graph. All right, so my first point, negative 1.44. So I know that this graph is tiny. This is negative 1 right here, and this is negative 2. So negative 1.44, let's see, 1, 2, 3, 4, 5. So right in the center would be negative 1.5, so a little bit before that. And I go up 3.6788. Notice these are counting by 1, so 1, 2, 3, so somewhere around in here. And then I have 0, 10, that one's easy. And then 1.44, so about halfway in between again, but up to 27. So my highest is at 30, so 25, 26, 27.183, so a little bit above that line, about right here, somewhere around in there. And this is going to get closer and closer to the x-axis, and then it's going to shoot up pretty quickly. It doesn't look like it's shooting up that quickly, but that's because I had to go with different scales with my x and my y so that y'all could see a good picture of it. But that's it. So now we could ask questions like, well, what about how big would the population be after 10 hours? And all we have to do is plug in a t of 10 and solve. So that would look like y equals 10 times e to the ln of 2 times 10. And when you put that into your calculator, you get 10,240, or approximately. So 10,240 bacteria after 10 hours of growth. So that's how it can be useful to you. Okay, the next concept that we study in this section is half-life. So the half-life of a particular compound is how long it takes for half of the radioactive decay to occur, which is decay of carbon-14. So we put an amount of time that it takes for the carbon-14 to reduce to half of its amount as the original specimen. One of the common terms associated with exponential, let me get back to my black pen here. Exponential, oh, that's a white pen, you can't see that. Exponential decay is known as half-life. And then that just describes what the half-life is. So define the half-life of a function. We still use the exponential growth model, which in its original form is A equals A sub 0 e to the kt. But notice we plugged in 1/2 A sub 0 because we're wanting to know, we want that output to be representative of when half of the amount of that initial carbon-14 is present. So we set A equal to 1/2 A sub 0, which A sub 0 is our initial amount. So if we want to solve this for time, that can be useful since a lot of times when you're dealing with exponential decay involved with half-life, you're wanting to know, well, how old is this thing? How long has this thing been decaying? So we divide A sub 0 off of both sides, and that leaves us with 1/2 equals e to the kt. We can now take the ln of both sides. Using our quotient rule for logarithms, the ln of 1/2 is the same thing as the ln of 1 minus the ln of 2. And that equals ln of e to the kt. That kt can now come out front as the coefficient. Also remember though, the ln of e, that's just 1. So that's going to go away, and all I'm going to have on the right-hand side is kt. Okay, the ln of 1 is 0, because I'd have to raise e to the 0 power to get 1. So all I really have left on the left-hand side is the negative ln of 2 equals kt. Now at this point, I can solve for k or I can solve for t. So if I want to solve for t, I just divide k off of both sides. And I get, to figure out the time that something's been decaying, I do the negative ln of 2 divided by my constant k. I could have solved for k and divided time off of both sides. So if I want to find my constant, that's just the negative ln of 2 divided by the time that that substance has been decaying. Okay, so let's use this practically. So we start off with the fact that the half-life of plutonium-244 is 80 million years. So it takes 80 million years for plutonium to decay to half its original amount. Wow. Find a function that gives the amount of carbon-14 remaining as a function of time. So we're trying to write a function that that models the carbon-14 decay in plutonium-244, or the half-life of plutonium-244. So I'll remind you that we want to fit it in that model. A equals A sub 0 e to the kt. And to write this function, all we need to know is the constant k. I don't need to know a starting, they haven't asked me to find out a particular starting amount, or they haven't given me a starting amount and asked me to find a new amount or a time. They just want the function that would give that to me. So the only thing I need to find is k. So k equals the negative ln of 2 divided by t, and t is the half-life, 80,000 years. I'm sorry, 80 million. So the negative ln of 2 divided by 80 million, when I put that into my calculator, I get negative 0.000000000877. Now, your calculator is not going to put all that on there. What it's going to do is it's going to say 8.76, blah, 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 and then it'll say e to the negative 9th. That means you've got to move the decimal place 9 places to the left to get what that number actually is. So be mindful of what your calculator is showing you. So now we can write the model for this situation, and the model is A equals A sub 0 times e to the negative 0.000000000877t. Okay, the next thing we're going to look at is radiocarbon dating. The formula for radioactive decay is important in radiocarbon dating, which is used to calculate the approximate date a plant or animal died. It is believed to be accurate within about 1% of error for plants or animals that died within the last 60,000 years. So actually, I was getting my radioactive decay and my half-life mixed up. Half-life, what we just talked about, that's for the substance to deplete to half its mass. And radioactive decaying is what's measuring the carbon-14. Hopefully that doesn't confuse you too much. So that's just my poor knowledge of science. Good thing I'm not your science professor. All right, so as long as a plant or animal is alive, the ratio of two isotopes of carbon in its body is close to the ratio in the atmosphere. When it dies, though, the carbon-14 in its body decays and it's not replaced. So by comparing the ratio of carbon-14 to carbon-12, which is what's in the atmosphere, in a decaying sample, to the known ratio in the atmosphere, the date the plant or animal died can be approximated. So since the half-life of carbon-14 is 5,730 years, the formula for the amount of carbon-14 remaining after T years is given by this particular function. And so all they did was solve for K. And don't freak out that that says the ln of 0.5, because remember that we found the ln of 1/2, and we figured out that that's the exact same thing as the negative ln of 2. Those two things are equal. And if you don't remember, just look back a couple slides ago and I showed you how that worked out like that. It's the quotient rule for logarithms that has that come about. Okay, so we start out with our equation for exponential growth. A equals A sub 0 e to the kt. And for this particular problem, I have already found my K value put in there for me. So I don't need to find anything. I'm ready to go ahead and start using my function. Scratch that. I'm going to show you how they got it. Couldn't figure out why I had just a blank general form here. I wanted to show you how they came up with that K value. So once again, we're talking about half-life. So on the left-hand side, we're going to replace A with 1/2 A sub 0. And that equals A sub 0 e to the K. And we know the time of the half-life is 5,730 years. So I'm going to start off by dividing off A sub 0 from both sides. And so I get that 1/2 is equal to E times the 5730K. And now I'm ready to take the natural log of both sides. So that left-hand side, so I'm about to show you how the ln of 1/2 is equal to the negative ln of 2, because that's the ln of 1 minus the ln of 2. And the ln of e raised to the 5730K, remember, that's just going to be 5730K. And the ln of 1 is 0, so negative 2, or negative ln of 2 equals 5730k. Divide both sides by 5730. And that is how we get that k is equal to the negative ln of 2 divided by, and this time it's 5730, our known half-life. Okay, so now we are ready to work with this function. Okay, so we are given cesium-137, and we're told it has a half-life of 30 years. If we begin with a 200 milligram sample of cesium or cesium, I'm not sure how that's pronounced, 137, probably cesium, will it take more or less than 230 years for it to reach only 1 milligram of mass? So what we're doing is we're going to be searching for time. We're going to be solving for time here. So we'll start out with our half-life version of the exponential growth function. 1/2 a sub 0 equals a sub 0 e to the kt. All right, so we know that we start out with 200 milligrams, and that's going to equal 200 e to the k times our half-life time, which is 30. So we're trying to find a value for k here. 1/2 of 200 is 100 e to the 30k. Divide 200 off of both sides. And that gives me 1/2 equal to e to the 30k, taking the natural log of both sides. Remember that the natural log of 1/2 is just the negative ln of 2. And the ln of e to the 30k is just 30k. Divide both sides by 30. And I get that for this particular problem, k is equal to the negative ln of 2 divided by 30. So you can see every time we're dealing with half-life, your constant k will always be the negative ln of 2 divided by the known half-life. So if you're given the half-life, you can go straight to your constant k. So now we want to figure out, well, let me actually rewrite our function now. So we have A, our new amount of our substance or population, equaling our initial times E. Our K is negative ln of 2 divided by 30, and that's multiplied by time. Okay, so the question that we were asked is when, basically, so we're going to be solving for t, will this be equal to 1 milligram? So I'm going to plug in 1 for my A value because that's what I'm wanting to see. I'm wanting to calculate, okay, how long did it take for it to decay all the way down to 1 milligram? My initial amount was 200 milligrams times e to the negative ln of 2 divided by 30 times t. Going to go ahead and take the ln of both sides. Oops, nope, I'm sorry, divide by 200 on both sides. and that gives me 1/200 equals e raised to the negative ln of 2 divided by 30 times t. I can now take the ln of both sides, the natural log. So notice I'm going to have the ln of 1 minus the ln of 200 on the left-hand side, but I know the ln of 1 is just 0. So this left-hand side becomes the negative ln of 200. The ln of e raised to the negative ln of 2 over 30 times t, well, at this point, that entire exponent comes down as the coefficient, and the ln of e is just 1. So the left side is now negative ln of 2 divided by 30 times t. Okay, so now to solve for t, I need to multiply both sides by the reciprocal 30 over negative ln of 2. Ooh, that looks bad, but you know what it is. I just said it. So, and this is negative 30 over the ln of 2. A little bit better on that side. So these divide out. So all I'm left with is t on the right-hand side. So my time that it took for my cesium-137 to degrade down from 200 to 1 milligram is equal to negative times a negative. So let me just note, these two things on the left-hand side are being multiplied. So a negative times a negative is a positive. And I forgot to write my negative here. Oh, no, never mind. Okay, so let me see if I can clean this up and make it look a little bit nicer. So I have 30 times the ln of 200 divided by the ln of 2. Phew. And when I put that into my calculator, I get approximately 229.32. So that is slightly less than 230 years. So less than 230 years. Slightly less than 230 years. Because the question was, will it take more or less than 230 years? It's going to take slightly, not much, but slightly less than 230 years. Okay, so here we go with a carbon dating. A bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is this bone? Okay, so specifically with carbon-14 dating, when we solve for t in that function or in that formula back a few pages, we get that that's the same thing as the natural log of a over a sub 0 divided by the negative natural log of 2 over 5730. Because remember, 5730 is the half-life of carbon. Okay, so a word about this A divided by A sub 0. This says, what do I want my ratio of final quantity to initial quantity be? What do I want that to be? I want that to be 20%. So I want to know, when will I end up with 20% of what I originally had, 20% of the carbon-14 that I originally had. So this is going to equal 0.2. So plugging all this information in, I get the ln of 0.2 divided by the negative ln of 2 divided by 5730. And when I put that all into my calculator, I get that my time is approximately 13,301 years, or 301.14 years. So my bone fragment, I'm going to put bone frag, is approximately 13,301 years old. Pretty interesting, huh? So for you forensics folks out there, you'll use this a lot. For you archaeologists, geologists, this is how they date things like that, whether it's bone fragments or pottery pieces from antiquity, whatever. Artwork is dated using carbon. Anything that you can that has been alive, plant or animal, you can use carbon dating to tell how long ago that particular thing was living. Okay, so the next time we look at, where we just got done looking at half-life, now we're going to flip-flop our thinking and thinking about calculating what they call doubling time. So for decaying quantities, we want to determine how long it took for half of a substance to decay. But for growing quantities, we might want to find out how long it takes for a quantity to double. As we mentioned above, the time it takes for a quantity to double is called the doubling time. So we start with that A equals A sub 0 e to the kt, but this time we want A to be twice whatever we started with, so that's doubled. So just like we did with the other formulas we worked with, we're going to divide that A sub 0 off of both sides. And that gives us 2 equals e to the kt. Take the ln of both sides. Those exponents come out front as the coefficient. The ln of e is just 1, so we don't write it. So I end up with the ln of 2 equals k times t, so I can either divide by k or divide by t. If I divide by k, I get t is equal to the ln of 2 over k. If I divide by t, I get that k is equal to the ln of 2 over t. So this is for doubling time. So here's a situation that might merit us using this particular formula. According to Moore's law, the doubling time for the number of transistors that can be put on a computer chip is approximately 2 years. In other words, every 2 years, the capacity of computer chips double, which is huge to think about. All right, so they want us to write a function that describes this behavior. Well, our function's going to come in the form of A equals A sub 0 e to the kt. So we just need to figure out, well, what's that constant that I need to plug in there? So for doubling time, k is equal to the ln of 2 divided by t. So in this case, k is equal to the ln of 2 divided by 2. And I've got my function. I'm ready to write it. My ending amount of resistors is equal to the amount, transistors is equal to the amount of transistors that I started with per chip multiplied by e to the ln of 2 divided by 2 times the amount of time, and in this case it's years, that it has been since the first computer chip was created. So that one was for all you computer science majors out there. All right, let's take a look at the law of cooling. So we'll go back to you chemists and maybe you biological scientists for this one. So we're given a formula, and I'm going to write it bigger here because I know it's difficult to see with how small I had to make it to fit it on the screen and on your notes page. We get T of T is equal to AE to the KT plus T sub S. So this is known as Newton's law of cooling. And what this does is it can either tell us how much time it will take for an object that has been put into a different temperature setting than what it is. So whether something is put into a refrigerator maybe and it's not already cold or at that refrigerator's temperature, or maybe you're pulling something out of the refrigerator so it's going from that cool temp to room temp. You can either tell how long it's going to take to reach a certain temperature, or you can know after this amount of time what temperature will that substance reach. So let me define the variables for you here. T is, of course, time. A is the difference between the initial temp or temperature of the object and the surrounding temperature. K is obviously our constant, and in this example, it's our continuous rate of cooling of the object. So this is our cooling constant, I guess. And T sub S is the actual surrounding or atmospheric temperature. Okay, so and T of T is our temperature after time. Once the object has been taken from one place and put into a different temperature setting. So we are given the example that we have a pitcher of water that's 40 degrees Fahrenheit, and it's, I guess, brought out of the refrigerator or whatever into a 70-degree room. 1 hour later, the temperature is 45 degrees. How long, so we're going to be solving for T, how long will it take for the temperature to rise to 60 degrees? Okay, so we're going to have to write or fill in this formula with specifics for our particular problem here. So here's what we do know. We know that at the 0 hour, the pitcher was 40 degrees Fahrenheit. So our pitcher was 40 degrees Fahrenheit. To the K times at the 0 hour. And then I have to add on my room temperature, 70. So I subtract 70 from both sides. And get negative 30 equals A times E to the K times 0 is E to the 0, and E to the 0 is 1. So my A value is going to equal negative 30. And think about this. Remember I just told you over here to the right that A is equal to the difference between the initial temperature of the object and the surrounding temperature. We started at 40, we subtract 70, and I get negative 30. This is how that happens. This is how that shows up, like it does in this particular formula. Okay, so now I have T of T is equal to A times e to the kt plus T sub S, my surrounding temperature. Okay, so I want to know, I know that 1 hour later, I'm 45 degrees. So I'm trying to find my constant K now. 1 hour later, I'm at 45 degrees. So I'm at 45 degrees. My A value is negative 30. E to the K, and it's 1 hour later times 1, plus my surrounding temperature, 70. So I subtract 70 from both sides. And I don't have room to write this all down, so I am not going to show that work. I'm going to try to be concise here. So this is negative 25 when I subtract 70 from both sides equals negative 30 e to the k, because k times 1 is just k. Divide both sides by 30. And on the left-hand side, I'll get negative 25 divided by negative 30, which reduces to positive 5/6 equals e to the k. I'm going to take the ln of both sides. And when I take the ln of the right-hand side, I just end up with k because that exponent comes out front as the variable, so I get my constant of cooling as the ln of 5/6. Okay, now I'm going to change colors here so that we don't get mixed up in the work. Hopefully I'll have room to finish. Now that I know my constant, I can say, well, to model any situation here, I have negative 30 times e to the ln of 5/6 times my time plus 70. And what the question is asking us is, okay, well, how long is it going to take to reach 60 degrees? So I want to know, when will this thing equal 60? So that's equal to negative 30 e to the ln of 5/6 times t plus 70. So I subtract 70 from both sides, and that gives me negative 10 equals negative 30 e to the ln of 5/6 t. Divide both sides by negative 30, and that gives me 1/3 equals e to the ln of 5/6 t. Take the ln of both sides, and don't forget that brings all of this out front as a coefficient. So I have the ln of 1/3. Oops, I changed back to black. Let me go to blue. The ln of 1/3 equaling, remember the ln of e is just 1, so on this side all I have is the ln of 5/6 t. So I need to divide the ln of 5/6 off of both sides. And I end up getting the ln of 1/3 divided by the ln of 5/6 equals t. And when I put that into my calculator, I get 6.026. So it takes approximately 6 hours for the pitcher of water to reach 60 degrees from 40 degrees. We've got one problem type left to look at. Okay, using logistic growth models. So this is the first logistic model we've looked at, and it's the only one we're going to look at. Exponential growth cannot continue forever. I mean, if you think about the exponential growth of a bacterial population, it's not going to always be exponential because other factors are going to come in with bacteria dying off, and then you've got all that to consider. So exponential models can be very useful for the short-term trends, but the longer they continue, the more they tend to fall apart. So they eventually have to approach some sort of limiting value where the growth is forced to slow down. For this reason, it's often better to use a model with an upper boundary instead of the exponential growth model, which is where we bring in a logistic or logarithmic growth model because they're approximately exponential at the first, but then they seem to just flatten out. And they approach an upper boundary. This upper boundary is called the carrying capacity. And that's for the constants noted in the formula here, A, B, and C. So we have our formula for a logistic growth model where it's going to shoot up very quickly, but then it's going to level off. One situation that uses this type of model regularly is pandemics. When we see, for example, here we have the flu and how it spreads to people. So let me just write our logistic growth model. F of x equal to c divided by 1 plus a times e to the negative bx. And in this particular model, c over 1 plus a is equal to our initial population, amount, whatever you have. I'm just going to put value, our initial value. C is the carrying capacity, and B is some constant. Okay, so in this particular problem, an influenza epidemic spreads through a population rapidly at a rate that depends on two factors. The more people who have the flu, the more rapidly it spreads. Also, the more uninfected people there are, the more rapidly it spreads. So, as people become infected, the more that are become infected, but the less that are uninfected, so it's not going to, that's why it caps off. It's kind of a rock and a hard place sort of situation if you think about it, because you've got one thing making it happen faster, but then that same thing is actually slowing it down. So this is why we use a logistic model to study the spread of communicable diseases. And clearly there's a maximum capacity or a carrying capacity because the only amount of people that can be affected are the amount of people in that population. So here's the situation that we're given to look at. We're told that at a t of 0, so at time 0, in some particular community of 1,000 people, so there's your carrying capacity right there. We're told at time 0, 1 person has the flu. So in that community, at most 1,000 people can have the flu because that's the size of the community. Researchers find that for this particular strain of the flu, the logistic growth model constant, so they're giving you this constant, is B equals 0.6030. Estimate the number of people, so we're going to be searching for f of x here, in the community who will have had the flu after 10 days of it spreading. Okay, so we start with our model. F of x equal to c over 1 plus a times e to the negative bx. Okay. So our initial value is equal to c over 1 plus a. Our initial population that we started out with was 1. So I need to solve here. Scratch this, we got to solve for a. So let's use our function over here. So we know that when this began at a t of 0, which in this case is x, so at an x value of 0, we had 1 person infected. So 1 equals, my carrying capacity is 1,000 people. There can't be more than 1,000 people affected in this community because that's how many people are in the community. 1 plus a times e to the negative b times 0, time of 0. That is 1 equals 1,000 over, okay, e to the 0 power is just 1. 1 times a is a, so this is just 1 plus a. So there's your c over 1 plus a, and that equals 1. So I can multiply both sides by 1 plus a. That 1 distributes, leaving me with 1 plus a on the left-hand side equals 1,000. So my a value, I subtract 1 and get 999. Okay, so the next question they ask is, okay, well, what about after 10 days? How many people are infected? So I plug into my function, f of x equals my carrying capacity, 1,000, divided by 1 plus, I now know what my a is, 999, times e to the, I've been given my b value, negative 0.6030, times my time, which is 10. And when I put all that into my calculator, I get that this is approximately 293.8507, so almost 294 people are infected at that time. Now, they also said, well, predict how many people in this community will have had this flu after a longer period of time has passed. So I just chose an amount. I was like, well, what about 1 month? We'll use 30 days. And I was surprised. So f of x equal to 1,000 divided by 1 plus 999, e raised to the negative 0.6030 times 30. And when I put all this into my calculator, I get, this is approximately 1,000, meaning that all people in the community will have had this flu at the end of 30 days. And I'm sure any of you with kids that go to a elementary school or even a middle school, you know that when one of them gets it, it spreads like wildfire. Well, that's all I have for you for 6.7. I have thoroughly enjoyed this semester with you, and I hope that these lectures have been helpful to help you really gain an understanding of functions as opposed to just memorizing something. I truly hope that understanding comes to you through your study of functions. Have a wonderful day.